So you click a link on your phone or you hit send on a message and boom, it's there. Have you ever actually stopped to wonder how that single command travels across the entire globe in just milliseconds? I mean, how exactly does a simple tap on a glass screen navigate this massive invisible highway of the internet to fetch information instantly? Well, welcome to this explainer. Today, we're going to completely decode the highly technical architecture of the internet. We're going to build it from the physical ground up, all the way to the code running on the screen you're looking at right this very second. Here is our roadmap for the journey. We've got 5 stops. First, physical devices and hardware. Second, protocols, or the rules of communication. Third, wireless and mobile connectivity. Fourth, navigating the web. And finally, the code behind the screen. All right, let's dive right into section 1, physical devices and the hardware. Okay, before data can just magically float through the air, it usually has to travel through physical wires. The absolutely crucial first step in any traditional network setup is the modem. See, your computer speaks entirely in digital data, but the outside telephone lines, they carry analog waves. So the modem acts as this real-time translator. It performs modulation, which means turning your computer's digital data into an analog signal to send it out, and then it handles demodulation, catching the incoming analog signal and translating it right back into digital data so your computer can actually understand it. Now, once that data gets into a local network, it has to be directed to the right computer. This is where we run into hubs and switches. Think of a hub as a dumb postman. If a hub receives a data packet, it has no idea who it's actually for, so just knocks on every single door, broadcasting the message to all the connected devices. As you can imagine, this shares the single bandwidth and causes a ton of unnecessary traffic jams. A switch, though, that's your smart postman. It actively reads the specific physical address, the MAC address, of the destination device and sends the data exactly to that one target. It gives you dedicated bandwidth per connection, meaning no unnecessary traffic. It is a bit more expensive, but it's a real game changer for speed. Moving right along to section 2, protocols, the invisible rules of communication. So, hardware alone just isn't enough. Our incredibly smart devices still need to know exactly how to talk to one another. Without protocols, all this hardware would literally just be shouting digital gibberish back and forth. A protocol is simply a set of formal rules and message formats that machines absolutely must follow to exchange data. It's basically their shared language. To see this in action, let's look at something you use every single day: email. Different tasks require completely different protocols, and it's all about a division of labor. SMTP is your sender. It pushes outgoing emails from your device to the server. Simple enough, right? But for receiving, you have 2 main options. POP3 downloads the email straight to your local computer and then deletes it from the server. It's great if you only check email on one device and want offline access. But IMAP is what allows you to view and manage emails while leaving them safely on the server. And that is exactly the protocol you rely on today to keep your inbox perfectly synced across your phone, your tablet, and your laptop. Okay, let's move to section 3, wireless and mobile connectivity. Obviously, we eventually wanted to cut those physical cords. And the evolution of mobile networks is this brilliant story of progressive revelation. Every single decade solved a completely new problem. Back in the 80s, 1G gave us analog voice calls, but absolutely zero data. Then the 90s brought 2G. This digitized the signal, meaning we finally got text messaging and some basic security. By the 2000s, 3G introduced broadband speeds, making basic mobile web browsing a reality. Then 4G stepped in and totally revolutionized our phones into high-speed, HD video streaming powerhouses. And now? Well, today's 5G isn't just about faster smartphones. With its ultra-low latency, it's actually the lightning-fast backbone for the Internet of Things, smart homes, and autonomous driving. Beyond cellular networks, when we want to connect our laptops wirelessly, we have to choose the right tool for the job, usually Wi-Fi or WiMAX. Wi-Fi is your standard short-distance solution. It's perfect for covering, say, 30 to 100 meters in your living room or a local cafe using basic encryption. But what if you need to provide internet to a massive rural area or an entire city? That is where WiMAX comes in. It functions like a giant, high-speed umbrella. It can cover fixed stations up to 30 miles away. That's roughly 50 kilometers. And it brings enhanced, multi-layered encryption along for the ride. Let's transition to section 4, navigating the web. So we're wirelessly connected, but how do we actually find what we're looking for? Under the hood, computers identify each other using IP addresses, which are just long strings of numbers. The problem? We humans are terrible at remembering long numbers. Enter DNS, the Domain Name System. Honestly, DNS is arguably the most helpful system ever invented for users. It acts as the automatic phone book of the internet. When you type in a domain name like google.com, a DNS server instantly looks up that name in its massive database and translates it into the exact numeric IP address the machines actually need to connect. And that builds right into the web addresses we type every single day. A URL, or Uniform Resource Locator, isn't just a random string of text, it's incredibly structured. First, it starts with the protocol or type, like HTTP or HTTPS, telling the server exactly how to communicate. Next up is the address, which is that domain name we just talked about, pointing you to the specific server. And finally, you have the path. Think of this like a filing cabinet directory. It points to the exact file or folder location on that server. Over time, what we actually find at those URLs has evolved drastically, basically in 3 massive steps. Web 1.0 was the first iteration. It was kind of like reading a digital brochure. The websites were totally static, built on simple HTML, with 0 user interaction. Then we moved into Web 2.0, which is the era we've lived in for the past couple of decades. This brought us dynamic content, social media, and heavy user participation where you actually generate the content. And now, we're shifting into Web 3.0. This next wave uses artificial intelligence, machine learning, and blockchain to create highly secure, deeply personalized, and super immersive experiences. Which brings us to our final stop, Section 5, the code behind the screen. To achieve all those rich, immersive Web 3.0 experiences, we need to peel back the very last layer, the complex programming that actually renders the web onto your screen. At the foundation, you'll often find 2 different markup languages, and it is absolutely crucial to contrast them. HTML focuses purely on presentation. It's the designer. It tells your browser how to lay out the text, where to drop the images, and how to format everything to make it look pretty. XML, on the other hand, doesn't care about presentation at all. XML is the strict organizer. It's used to define data structurally. It simply labels exactly what the data is, so that databases and external programs can safely read and exchange that structured information. But you see, HTML alone is totally static. To make pages dynamic, developers use scripts. And this workload is brilliantly split into 2 camps. First, we have client-side scripting, which runs right inside your browser. Because this code is downloaded directly to your device, it gives you an immediate response without needing to reload the page. It's perfect for things like interactive forms or cool hover effects. However, because the code is sitting right there on your machine, it's visible and inherently less secure. For the real heavy lifting, we use server-side scripting. This code executes on the web host server completely out of sight. Now, it is a bit slower because your browser has to wait for the server to process the request and send the result back, but it is highly secure. This is exactly what's running behind the scenes to protect your passwords or pull sensitive information from a database. Well, we've built an incredible roadmap today. We started with the physical modems and those smart postman switches, layered on the strict protocols of email, cut the physical cords with generational leaps in wireless tech, navigated the web via the DNS phone book, and finally we dug into the delicate dance of HTML, XML, and server-side scripting that brings a web page to life. Knowing how this invisible highway was systematically built, block by block, from heavy metal cables all the way up to AI-driven dynamic Web 3.0 code, I want to leave you with this thought. What revolutionary building block will be added next? When we look forward to the wild potential of 6G and Web 4.0, what completely new architecture will be required to keep us connected? Thank you so much for exploring this with me today.